Alright, hi chemistry class. This is Monday of week 4. It is May the 18th and it's day 59 on our course schedule. So last week we did kind of an intense subject, a lot of math. Hope that a lot of it came through to you. This week we're going to deal with what are called phases of matter and gas laws. And what phases of matter means is, if you think of water, you all know it's H2O. But H2O can be in different states of matter. It could be ice, which is frozen water, or it could be liquid water. And if you eat an ice cube or if you drink a glass of water, your body doesn't know the difference. One's colder than the other, but they're both H2O. The way they react chemically in your body is the same because it's the same chemical substance, H2O. But they're different. What do you call that difference between ice and water? It's not chemically different, but it's physically different. That's called a physical difference. And so what we're going to do is talk about what causes phases or states of matter, as they're sometimes called, which is either a solid, a liquid, or a gas. And in the case of water, the solid would be ice, the liquid would be liquid water, and the gas would be steam or vapor. So that'll be the subject of today's lesson. So let's review chemical bonds because they're so central that the more we review them, the better. We talked about that there's only 90 different types of atoms in the entire universe, which is an amazing fact. The second amazing fact is that those 90 different types of atoms can form tens and tens of millions of different types of substances by combining. And there's only 3 different ways that they can combine. That's another amazing fact. So let's review those. The first is called metallic bonds. And remember, there's 2 broad groups of elements on the periodic table. There's metals and nonmetals. So metallic bonds form between metals and nonmetals. And what they are is, if you take copper, for example, a piece of copper wire, it has just copper atoms in it. And so those are atoms that all have the same electronegativity and ionization energy because they're the same. And they also have a large number of orbitals. And that means their electrons, their valence electrons, are far away from the nucleus. And therefore, they can very easily swap from one copper atom to the next. They can just as easily be attracted to the next copper atom. And this causes them to just kind of run around kind of freely, like you see on the screen there. It's called the electron sea model because it's kind of like fish swimming around in the ocean. And that's the way electrons move. And that constant changing polarity between having negatives in one place and then in another and then in another is going to cause the atoms to bond together. So that's a metallic bond. Next is the ionic bond. We talked quite a bit about that. And that is between a metal and a nonmetal. So a metal such as sodium, which has a low ionization energy, when it comes near a nonmetal such as chlorine, which has a high electronegativity, meaning it wants to pull in electrons, the low ionization sodium, which wants to give up electrons, will pass an electron over to the chlorine. And that makes the chlorine a negatively charged anion, the sodium a positively charged cation, and they attract each other to form NaCl, which is just table salt. But you don't find NaCl as a separate object, one Na and one Cl. They form like bricks in a wall, like you see in that little cube down below, or the other analogy I use is like apartments in an apartment building. You can tell one from the next, but they're not separate. You can't just take an apartment and pull it out of an apartment building, or take a brick and just pull it out of a brick wall. But you can see one brick from the other and one apartment from the other. So they've called NaCl is what's called a formula unit, meaning it's the smallest basic unit of relationship between sodium and chlorine in salt. But they're not separate individual objects. Now we move over to covalent bonds, and those are between 2 nonmetals. And you may remember the metaphor of 2 strong guys having a tug of war. They both have high electronegativity. They like to pull in outside electrons. They both also have high ionization energies. They don't like to give up their electrons. And therefore, they agree to share electrons. So the hydrogen and the oxygen will share electrons, fulfilling the octet rule. And that's a covalent bond. Now, what covalent bonds form is independent structures called molecules. So whereas the Na and Cl are like apartments in an apartment building or bricks in a wall, the molecules of a covalent bond are separate independent structures. They can move around separately like cars. You can think of a car going in one direction, a different car goes in a different direction. The same is true of molecules. And so those are the 3 types of bonds and the structures that they form. So if we take these three types of bonds, when we talk about intermolecular forces and states of matter, we're really just talking about one type, and that's covalent bonds. It's not that metallic and ionic bonds can't form gases, liquids, and solids, but generally at this level of chemistry, we're talking about in terms of covalent bonds and separate independent molecules. So only covalent bonds form separate structures called molecules. Intermolecular forces determine whether molecules stick together or not. So the key point is that intermolecular forces are much weaker than covalent ionic or metallic bonds. So the fact that hydrogen is attracted to the oxygen is a covalent bond. That's a chemical bond. It creates a new chemical structure called water. But the fact that two water molecules want to stick together, that's an intermolecular force. Two water molecules sticking together doesn't form a new chemical structure. It just means you got two water molecules that don't have enough energy to break apart and that want to stick together. So you don't have a new chemical substance due to intermolecular forces. Intermolecular forces simply determine the states of matter, solid, liquid, or gas, of a particular substance. So let's look at this. You've probably had this in middle school, even elementary school. So solids retain its own shape, like those ice cubes. It's incompressible, you can't squeeze it down, and it doesn't flow. If those ice cubes don't melt, if they're cold enough, they're not gonna move. They're not gonna flow anywhere. Liquids take the shape of the container, so you could have a tall, narrow glass or a short, wide glass and have the same amount of water. They're also incompressible, though, just like a solid. So if you try to squeeze on water, the water molecules are right next to each other. They're just kind of looser than they are in a solid, but they're just as close together. And in the case of water, you'd be surprised to know, we'll learn this later, they're actually closer together in liquid water than in solid water. And therefore, they're incompressible. You can't squeeze them. And they diffuse slowly in other liquids. They spread out more slowly. Gases take the size and shape of a container. So if you think of a bottle of strong perfume, and it's all the molecules of perfume are inside that bottle. But if you take the cap off on take the lid off on a hot day, those molecules will spread out throughout the room. You'll be able to smell them everywhere. So they've moved from taking on the size and shape of the bottle to taking on the size and shape of the room. So that's what that concept is. They flow and they diffuse in gas rapidly. They can spread around easily because they're spread out. Gas molecules are spread out. Okay, so the whole subject of intermolecular forces, whether water forms ice, liquid water, or gas, has to do with this battle between intermolecular forces versus kinetic energy. So IMF, intermolecular forces, are a battle between kinetic energy and Coulombic attractions. So Coulombic attractions are the electrostatic forces of protons and electrons that attract molecules to each other. So they would attract the positive end of one water molecule to the negative side of another water molecule. Those are the Coulombic attractions. But they're very weak, much weaker than covalent bonds are. Kinetic energy, on the other hand, is something that comes from the outside. It could come from the sun, it could come from a stove, and kinetic energy in the molecules is caused by higher temperature and assisted by lower pressures that allows the molecules to separate. So whichever one of these two things predominates will determine the state of the matter. So if the kinetic energy, in the case of water, if kinetic energy predominates, the water will become vapor, it will become steam. If, on the other hand, there's very little kinetic energy, the Coulombic attractions between the water molecules will predominate, and they'll either become liquid or even solid if it's cold enough. So generally, matter moves from gas to liquid to solid. That is, the molecules are coming closer together in two ways. One is by reducing the temperature so the molecules decrease energy and move closer together. They don't have enough energy to break away from each other anymore. So if you start at 20 degrees, which is roughly room temperature, and then you go down to 0 degrees, which is freezing, then these two molecules, which are vapor right now, water vapor, will eventually settle in and they'll be attracted to each other. The positive end of one is attracted to the negative end of the other water molecule. The other way that you can bring them together is just by brute force, by increasing the pressure while keeping the temperature constant and squeezing the molecules closer together. So if you imagine that that's a cylinder and a piston up on the top there, and you just squeeze the piston down, then it just squeezes the molecules tighter together. So that's another way to bring the molecules and to turn them into a solid or a liquid. All right, if the kinetic energy overwhelms the Coulombic attractions, then the molecules separate and exist as gas or vapor. So they still have their positive end and negative end. That hasn't gone away. They still have the same Coulombic attraction. It's just it's overwhelmed by the kinetic energy, which allows them to break away from each other, and not only from each other, from the Earth, from gravity. They're allowed to float up into the sky, into space. Okay, if the kinetic energy and the Coulombic attractions are about equal, then the molecules stick together but can move around each other. So these molecules would be indicative of a liquid. They're staying together, they're not separating, so they are incompressible. You can't squeeze them any tighter together, but they are free to move around each other. And that would be an example of how liquid molecules of water move. And finally, if the kinetic energy is low compared to the intermolecular forces, then the molecules will stick together in fixed places, and this produces a solid. Molecules, even in a solid like a metal, like iron or anything like that, the molecules are still moving. Even in ice, liquid water, looks like nothing's moving. Those molecules are moving, but they can't move apart and they can't move around each other, but they can wiggle like this. And if you put heat into them, they'll start wiggling faster. They'll have greater kinetic energy. So what is temperature? Temperature is the average kinetic energy of particles of matter, such as atoms or molecules. Kinetic energy is the energy in a moving object and is determined by the mass of an object and how fast it's moving. So you may remember from physics the formula is 1/2 mv squared, mass times velocity squared. So it's a function of both how big and heavy the molecule is or the object is and how fast it's moving. That's kinetic energy. But again, even in solids, the atoms or molecules do move, and so they therefore do have kinetic energy. So let's talk about the different states and changes of states in matter. So solid turning to liquid is melting, and liquid turning to solid is freezing, if we think of water or any other substance. So you're familiar with those terms. Those are common everyday terms. On the other side, if you go from liquid to gas, that's called vaporization. And if you go from gas, water vapor, for example, back down to liquid, that's called condensation. That's why you see water on the leaves in the morning, and on cars and on objects early in the morning. So that's condensation. Okay, if a solid turns directly into a gas, this is very unusual, it's called sublimation. So an example of that you've all seen, and I wanted to do in class, but we unfortunately don't have the chance, is the steam coming off of dry ice, which is frozen carbon dioxide. It creates all that smoke, and it's really just carbon dioxide vapor. So it doesn't melt into liquid carbon dioxide. It simply goes from a solid directly to a gas. And then gas turning directly into a solid is called deposition. That's not a very well-known term, but that would be going in the other direction. Okay, now, the amount of energy that either goes into the substance or comes out of the substance to change it from one phase to another, there's two different types. There's the heat of fusion, and the word fuse technically means to stick together, bring something together, to get something to stick together. So, but it's called the heat of fusion whether it's melting or freezing. So if you melt ice, you need a certain amount of heat to get the ice to melt. And this is known, the heat of fusion and heat of vaporization are known for all substances. So water has a very specific, well-known heat of fusion. It's the amount of heat that you would have to put into 1 mole of ice to cause it to melt into liquid water, or it's the amount of heat you'd have to take out of 1 mole of liquid water to get it to freeze into ice. If you want water to turn into ice, you have to pull the heat energy out of it so the water molecules will stick together. But anyway, the amount of heat that is for 1 mole is called the heat of fusion. On the other side, the amount of heat required to turn liquid into steam, 1 mole, is called the heat of vaporization. And if you go in the other direction from steam or vapor back to liquid, that's called condensation. It's still the same amount. The numeric value is the same, it's just opposite sign. When you're making the molecules go from steam to liquid, you're taking heat out. When you're making the molecules go from liquid to steam or to vapor, you're putting the heat in. The English or Fahrenheit system of temperature measurement is the one we use here in the U.S. The units of measure of temperature in the English system is degrees Fahrenheit. On the English system, water freezes at 32 degrees Fahrenheit and water boils at 212 degrees Fahrenheit. So I've been asked why are these numbers, and I've read a number of explanations. It's not really important because we're not going to deal with this system. Okay, the metric system's temperature measurement is the one used in most of the rest of the world, as well as in chemistry and other sciences. The units of measure for temperature in the metric system is degrees centigrade or Celsius. Celsius is a man's name, is a person's name. Centigrade just means 100 divisions or 100 gradations. And so what they simply did is they said, okay, what's the freezing point of water? What's the boiling point of water? Let's just break that into 100 pieces, and we'll call that a degree centigrade on the centigrade scale. So it's not a coincidence that the freezing and boiling points are 0 and 100. They were actually defined around the property of water and where water freezes and where water boils. The Kelvin system of temperature measurement is one that defines 0 as the temperature at which the object has no energy. It's a dead atom. It's got no energy in it anymore. 0 on the Kelvin scale is called absolute zero. It is impossible to have a temperature lower than 0 on the Kelvin scale. The units of measure of temperature on the Kelvin scale is called kelvins. They don't call it degrees Kelvin, not really an important point, but it's not called degrees Kelvin, it's just called kelvins. So important, a degree on the centigrade scale is exactly the same as a degree on the Kelvin scale. The scales differ only in what they define as 0. So in other words, if you look at let's go ahead and let's look at the Kelvin scale and you'll see what that means exactly. Okay, the unit of measure of temperature in the Kelvin system is the same degree as that used in the metric system. So on the Kelvin scale, water freezes at 273 and water boils at 373 Kelvin. So you'll notice there's a 100-degree difference between the freezing point and boiling point of water, just as there is on the centigrade scale. It's just that they have a different definition of what 0 is. Now to convert from one to the other is pretty easy. To get from centigrade to Kelvin, you just add 273 to the degrees Kelvin, or to the degrees centigrade. And to go the other direction, you can see the equation there. So the example, convert 20 degrees centigrade to Kelvin, you just add 20 plus 273 gives you 293 Kelvin. Convert 303 Kelvin to centigrade, you take 303, you subtract 273, and you get 30 degrees centigrade. And these two scales side by side show you kind of how they relate to each other. So you can see the freezing point and boiling point of water. It's a 100-degree difference on both scales, from 0 to 100 on the centigrade scale and from 273 to 373 on the Kelvin scale. So a degree on each scale is the same amount of temperature change. The difference is that centigrade scale is more designed for everyday use in our everyday world, because we tend to live in temperature ranges between 0 to 100 centigrade. Whereas the Kelvin scale defines 0 as the absolute lowest possible temperature in the universe. You cannot go lower than 0 on the Kelvin scale. And so that's something that scientists who work with gases that become liquids at minus 200 or 250 degrees, they need a scale that goes down there. So there's no negative numbers on the Kelvin scale, because the lowest possible value of temperature in the universe is 0 Kelvin. Okay, so that wraps us up for today. We're going to go on and talk about the difference between heat and temperature tomorrow, and then move on to talking about gases and some of the properties of gases on Wednesday and Thursday. So have a good day, and get in touch with me if you have any questions.